Calculating voltage drop involves several steps. Firstly, determine the circuit parameters, specifically the distance in feet, the amperage in amps, and the wire size in American wire gauge or AWG. Secondly, find the resistance per foot of the wire. This is achieved by using the National Electrical Code or NEC Table 8 in Chapter 9 for direct current or DC resistance of conductors. Locate the wire size and conductor type in the table. Then, read the resistance per foot measured in ohms per foot. Thirdly, calculate the total resistance of the circuit. To do this, multiply the resistance per foot by the distance. The formula is total resistance equals resistance per foot times distance. Fourthly, calculate the voltage drop. Multiply the total resistance by the amperage. The formula is voltage drop equals total resistance times current. The NEC does not provide a specific formula for calculating voltage drop. However, it does provide the resistance values in Table 8, which are used in the calculation. An alternative formula for voltage drop is voltage drop equals distance times current times resistance divided by voltage times 1000, where voltage is the supply voltage in volts, resistance is the total resistance in ohms, and 1000 is a conversion factor from feet to meters. Here are some tips. Firstly, use copper wire as it has lower resistance than aluminum. Secondly, choose a wire size that is appropriate for the amperage. Thirdly, keep the distance as short as possible to minimize voltage drop. If the voltage drop exceeds 5%, consider using a larger wire size or a different circuit design. Now let's delve deeper into understanding each of these steps with more detail. Firstly, regarding determining the circuit parameters, accurately measuring the distance is crucial. Use a measuring tape or a laser distance measurer to get the correct length of the wire run. The amperage should be the maximum expected current that the circuit will carry. Check the nameplate of the equipment or appliances connected to the circuit, or consult relevant tables for estimating the load. The wire size is typically specified by the design or local electrical codes. Make sure to note it accurately. Secondly, when finding the resistance per foot of wire using the NEC Table 8, understand that this table provides DC resistance values. For alternating current or AC circuits, the impedance might be different due to factors like skin effect and proximity effect. However, for most general applications, the DC resistance is a good approximation. When looking up the values, ensure you match the conductor type correctly. Common types include copper and aluminum, and each has different resistance characteristics. Be precise in reading the ohms per foot value from the table to ensure accurate calculation. Thirdly, regarding calculating the total resistance of the circuit, it is a straightforward multiplication. Ensure that the units are consistent with the distance in feet and the resistance in ohms per foot to get the total resistance in ohms. This step is vital because even smaller errors here can compound in the final voltage drop calculation. Fourthly, for calculating the voltage drop, multiplying the total resistance by the amperage gives the voltage drop in volts. The voltage drop represents the amount of voltage loss along the wire due to its resistance. This loss can affect the performance of connected equipment, especially sensitive electronic devices. Now let's elaborate on the alternative formula. Voltage drop equals distance times current times resistance divided by voltage times 1000. This formula provides a more direct calculation, but it still relies on accurate inputs. The voltage in this formula is the source voltage of the circuit. The resistance is the total resistance of the wire, which can be calculated from the ohms per foot and the total length, as explained earlier. The constant 1000 is used for unit conversion, assuming the distance is in feet. It is essential to use consistent units to avoid errors. The tips provided earlier are practical guidelines to minimize voltage drop. Firstly, using copper wire is advantageous because copper has a lower resistivity than aluminum, meaning it offers less resistance to current flow for the same wire size. This results in less voltage drop over a given distance. Secondly, choosing an appropriate wire size is crucial. Larger wire sizes have lower resistance. Consult the NEC tables to determine the minimum wire size required for the given amperage to ensure it meets safety standards and minimizes voltage drop. Thirdly, keeping the distance as short as possible is a straightforward way to reduce voltage drop, because the longer the wire, the greater the resistance and consequently, the greater the voltage drop. Finally, monitoring the voltage drop and taking corrective action if it exceeds 5% is essential. If the voltage drop is too high, equipment may not function correctly, and it can also lead to overheating and potential safety hazards. In such cases, consider using a larger wire size, shortening the circuit length, or redesigning the circuit. Let's also consider some practical scenarios where these calculations and tips are invaluable. In residential wiring, understanding voltage drop is essential for ensuring that appliances and electronic devices receive the correct voltage. This is especially important for long wire runs, such as those to detached garages or outbuildings. In commercial buildings, voltage drop can affect the performance of lighting systems, motors, and sensitive equipment. Proper calculation and mitigation are vital for efficient and reliable operation. In industrial settings, where heavy machinery and equipment are used, voltage drop can lead to significant performance issues. Careful planning and design are necessary to maintain stable voltage levels throughout the facility. Moreover, let's explore some additional factors that can influence voltage drop. Temperature affects the resistance of conductors. As the temperature increases, the resistance also increases, leading to a higher voltage drop. This is particularly relevant in high-temperature environments. The type of insulation used and the wire can also impact voltage drop. Some insulation types have better heat dissipation properties, which can help to keep the conductor cooler and reduce resistance. The method of installation can also play a role. Wires bundled together in a conduit may experience higher temperatures due to reduced heat dissipation, which can increase resistance and voltage drop. Furthermore, understanding the concept of voltage drop is crucial for complying with electrical codes and standards. The NEC provides guidelines for maximum allowable voltage drop in different types of circuits. Adhering to these guidelines ensures safety and optimal performance. Now, let's talk about the tools and resources available to assist with voltage drop calculations. There are numerous online voltage drop calculators that can simplify the process. These calculators typically require inputs such as wire size, amperage, distance, and voltage, and they provide an instant result for voltage drop. There are also software applications that can perform more complex voltage drop analysis, taking into account factors such as temperature, conductor type, and installation method. These tools are particularly useful for large-scale projects and complex electrical systems. In addition to calculators and software, there are also numerous resources available to learn more about voltage drop, including textbooks, online courses, and industry publications. These resources can provide a deeper understanding of the underlying principles and practical applications of voltage drop calculations. Let's also consider some common mistakes to avoid when calculating voltage drop. One common mistake is using incorrect values for wire size or amperage. Double-checking these values is essential to ensure accuracy. Another mistake is neglecting to account for the resistance of connections and splices. These connections can add to the overall resistance of the circuit and increase voltage drop. A further mistake is failing to consider the impact of nonlinear loads such as electronic devices and fluorescent lighting. These loads can generate harmonic currents that increase voltage drop. Now let's consider the impact of voltage drop on different types of equipment. For lighting systems, excessive voltage drop can cause dimming and reduce light output. This can affect visibility and safety. For motors, voltage drop can reduce torque and efficiency. This can lead to overheating and premature failure. For electronic devices, voltage drop can cause malfunctions and data loss. This can be particularly problematic for sensitive equipment such as computers and medical devices. In summary, calculating voltage drop accurately is essential for ensuring the safety, reliability, and efficiency of electrical systems. By understanding the principles and following the steps outlined earlier, you can minimize voltage drop and optimize the performance of your electrical circuits. Remember to use the NEC tables, online calculators, and other resources to assist with your calculations and to stay informed about the latest codes and standards. Voltage drop calculation is fundamental in electrical engineering, impacting the design and operation of electrical systems. A well-designed system minimizes voltage drop, ensuring that equipment receives the necessary voltage to operate efficiently and safely. The effects of excessive voltage drop range from reduced performance to potential equipment damage. Understanding the factors that influence voltage drop, such as wire size, conductor material, current, and distance, is critical for effective system design. Let's consider the wire size influence. Larger diameter wires have lower resistance, reducing voltage drop. NEC tables provide guidance on the appropriate wire size for various current levels and applications. The choice of conductor material matters, as copper is generally preferred due to its lower resistance compared to aluminum, but aluminum may be used in some applications where weight is a concern, requiring a larger wire size to achieve similar voltage drop performance. Current level is also an important consideration, as high currents cause greater voltage drop. Careful calculation of the expected current is essential for selecting the proper wire size. Distance also directly impacts voltage drop, with longer runs experiencing greater voltage drop. Minimizing circuit length is an effective strategy for reducing voltage drop. Accurate voltage drop calculation is essential for compliance with electrical codes, which specify maximum allowable voltage drop to ensure safety and performance. Additionally, selecting the right tools and resources for voltage drop calculation is important. Online calculators and software can simplify the process and improve accuracy. Always verify the results and understand the assumptions behind these tools. Now let's discuss practical applications of voltage drop calculation. In residential settings, it is important to calculate voltage drop to ensure that appliances and lighting operate efficiently. Long runs to detached garages or workshops are particularly susceptible to voltage drop. In commercial settings, voltage drop can impact the performance of sensitive electronic equipment and lighting systems, with careful design and calculation needed to minimize voltage drop in long-branch circuits. In industrial settings, voltage drop can affect the operation of motors and other heavy machinery, with proper voltage drop calculation vital for ensuring reliable operation. When designing electrical systems, consider the trade-offs between different approaches to minimize voltage drop. Increasing wire size reduces voltage drop but increases material costs. Shortening circuit length reduces voltage drop but may require relocating equipment. Optimizing circuit layout and component selection is crucial for achieving the desired performance at a reasonable cost. Now let's cover some advanced considerations in voltage drop calculation. For alternating current circuits, impedance, which includes resistance and reactance, must be considered. Reactance arises from the inductance and capacitance of the circuit and can affect voltage drop. Harmonic currents, produced by nonlinear loads, can also contribute to voltage drop. Understanding the characteristics of the loads connected to the circuit is important for accurate voltage drop calculation. Additionally, temperature variations can affect conductor resistance, so consider operating temperature when calculating voltage drop, especially in high-temperature environments. When troubleshooting voltage drop problems, start by verifying the circuit parameters such as wire size, length, and current. Use a multimeter to measure voltage at various points in the circuit and compare the measured values to the calculated values. Look for loose connections or corroded terminals, which can increase resistance and voltage drop. The NEC provides guidelines on acceptable voltage drop levels for different types of circuits. Consult the code for specific requirements. Understanding the principles of voltage drop and applying them correctly is essential for designing and maintaining safe and efficient electrical systems. Continuous learning and staying up to date with the latest codes and standards are crucial for electrical professionals. Consider attending training courses and workshops to enhance your knowledge and skills in this area.